three types. One is exponential growth. All these models will be given to you. If they're not, you can ask during the test, I'll give it to you. Because some of the problems in MyLab Math may not, but I'll give you the models. I'll write them from the very beginning on paper. Okay, so the exponential growth is A of t equals A0 e to kt. We've seen this before. This is the same model with continuous compound interest. So this is the number. This is the original. This is, of course, the number or the amount at time t. Of course, this is our friend E from the calculator. Euler's number is called. K is the growth rate. And this is time in years. So this is the annual. The annual growth rate, time in years, everything is the same that we had before. The original value, or the starting point, the initial value if you want, the original or the starting point, and this is at time t. Number two is the exponential decay. Everything the same, there is only one difference. This is the only difference. The difference is that this has minus in front of k and this one has plus in front of k. Everything the same. The mass or the number at time t, the original value or initial value or beginning value, t is the time in years, and k here is not called the annual growth rate, but it's called the decay rate. That's the only difference. And the third possible model is called logistic growth. So all models will be given to you. I want to start with number 3. On page on page 530, let's start with problem 37. You will see a general pattern in all these problems. So the logistic, this is at C here. Logistic. Okay, so we're looking at f of t equals 100,000 divided by 1 plus 5,000 e to negative t. And this is problem 37 on 530. Okay, so let's read the problem. It's a problem in fashion these days. The logistic growth function given to us describes the number of people, f of t. I take notes. Number of people who have become ill with the flu, t weeks. T is the number of weeks after its initial outbreak in a particular community. And we have 3 questions. Part A, how many people became ill with the flu when the epidemic began? Initial value, initial number. How many people were ill by the end of the 4th week? 4th week. What is the limiting size of the population? We'll talk about that. So we put this away. It's so heavy. Okay, so we're given a function. We are specifically told that t is time in weeks, and this is the number of people that become ill. and the function is, or the model, the logistic growth model is given to us. We're asked to find the initial number of people who got the flu. When we're asked about the initial number, what does that mean? What are we really asked to do in part A? What are we asked to find? We're asked to find f of 0. What happens? What is the initial number, the original number of people who got the flu? So when I plug in 0, e to 0 is 1. 1 times 5,000 is 5,000. 5,000 plus 1 is 5,001. So initially 100,000 divided by 5,001. And I cannot round up when it comes to people, or cats, or bats, or mice, or whatever. So 100,000, I shouldn't do this with the calculator, but anyway. So 5,001. So it's 19.99. I can't say 20. Even if they ask you to round whatever, I really can't say 19.99. It doesn't mean 20 people. Okay, so I will say 19 people. If they ask you to round up, then you're going to say 20. But when it comes to people, I can't really say. 19.99 is not 20 people. Anyway, good. So now for the 4th week, I'm asked to find this. So this is part B, f of 4. So I just plug in 4. So I have 100,000 divided by, in parentheses, careful, 1 plus 5,000 times e. Remember where e is, to a power, in parentheses, negative 4. Close the parenthesis for the numerator, for the power, and close the parenthesis. Remember, we need parentheses around the denominator. So close the parenthesis for the denominator, and I press enter, and I have 1,080 people. So 1,080 people were sick by the end of the 4th week. That's why we stay indoors. Okay, so when it comes to the limiting size of the population, we are really asked to find the trend. In other words, when time goes to infinity, number of weeks passes, more weeks, where does f of t go? That's what we are asked to determine. It's the end behavior. So let's put in the function in the graphing calculator, 100,000, and y equals, please. Now the function, because we want to plug in more than one value, divided by, in parentheses, 1 plus 5,000. Stop me if you fall behind or you need help with this. Second and e again, in parentheses, negative x, close the parenthesis, and close the parenthesis for the denominator. And now I can plug in whatever I want. Not exactly. I cannot plug in negative 5 because time is not negative. So, but of course I can get the same numbers I got before. So when I plug in 0, I got 19.99. When I plugged in 4, that's why I like this system. And now the time passes. Okay, 8 weeks later, 9 weeks later, 12 weeks later, 50 weeks later. What do we notice? Can anyone tell us, what do you notice?
Eventually all the numbers become 100,000. They don't go any higher.
Thank you very much. That's all I needed. So that is, indeed, maximum number of people that can get ill. That's why we stayed indoors, because the maximum number, and we didn't travel anywhere, the maximum number was just the number that we are in each individual city or location. It couldn't get more unless we had visitors or we went somewhere else. So this was a logistic growth model. Any questions for me on the logistic growth model before we look at the other two? I forgot my pitcher of water. I'll be just right back. I got it. now I have it handy. Any questions? Any questions on the logistic growth model? Anyone?
Is it true that the limiting factor is f of t equals c? Like whatever t is, then that is the limiting factor?
You mean the numerator? Yes, because y equals 100,000 is the horizontal asymptote of the function. If you graph it, you'll see. Yes. Ben, I got your question. Can we talk about it today? I responded. Did you get my email?
I did, and I rewatched that video because I had watched it previous to emailing you.
Right, but I would like to work on that problem for everyone.
Yeah, that would be helpful. Thank you.
Very good. I have it handy. I have it in my email. And I know I didn't close my email. I think it's still open here. Yes, it is. But I think I'm not there yet. Let me see if I remember correctly what your question was about. Because the link disappears after a while, so I just was hoping that it's still there.
Oh, do you want me to dig through my email and see if I can find
Oh,
it?
no, I found it. I found it, and the link is still there.
Okay.
It's just that it needs a second to open. Yes, it was about the half-life. I need another 10 minutes, and then we'll work on that problem. Is that okay?
Yeah, that's great. Thank you.
Good, very good. Okay, any questions on the logistic growth model? Do we need another one? Okay, let's do another one. I didn't hear anything, but let's do another one. Like, I'm looking at problems 44 and 46 on page 531, and we have, we have P of x, sorry about that, which is 90 divided by 1 plus 271 e to negative 0.122x. So this is another logistic growth model. And let's see what they're asking us, or what, first of all, what the variables represent, and then to answer the questions. They're telling us that P of x is the percentage of Americans who are X years old with some coronary heart disease, and X is the age. What percentage, in 44, what percentage of 20-year-olds have some coronary heart disease? So for X equals 20, we're asked to find the percentage of people, and we expect the answer to be very low. So we will put in the graphing calculator, put in the functions, and so it's just one value, that's okay. We can just calculate it as 90 divided by, in parentheses, 1 plus 271. E, remember where E is, please, in parentheses, negative 0.122 multiplied by 20, close the parenthesis for the power and close the parenthesis for the denominator. It may not require parentheses around the power, but I always like to be cautious with that. So about 4%. So about 4% of the 20-year-old age group have some coronary heart disease. Problem 46. Oh, of course, I did 43. Sorry. 43. Okay, so this is 43. So now let's look at 46. In 46, we're asked, at what age is the percentage of some coronary heart disease 70%? So here we're asked to find what is x when p is 70. So this is not a trivial type of problem. Careful here. We replace x by p of x by 70. 90 divided by 1 plus 271 e to negative 0.122x. So the first thing we have to notice is that this is really a proportion. Once you notice that it's a proportion, it becomes, let's say, step by step, somewhat easier. So I see that 70 times this, do not multiply, just leave it outside. 1 plus 271e to negative 0.122x equals 1 times 90. Obviously, the next step here is to divide both sides by 70. Remember, I have to solve for this, eliminating everything, so I can apply natural log. So when I divide both sides by 70, I get 9 over 7. In the next step, I have to remove the 1, subtracting 1 from both sides. 9 over 7 minus 1. And I know that this is 9 over 7 minus 7 over 7, so this will be 2 over 7. And now I have to divide by 271. I had to completely clean it up. So at the top, 2 over 7, in the denominator, 271. Don't bother with this. Don't even look at it. It's a number. We'll take care of it later. Okay, so at this point, I have to apply natural log to both sides to bring the power down. So natural log here and natural log here. So negative 0.122x. I should write times natural log e, but why don't we write natural log e? It should be here, times natural log e. How come that I don't write that?
Because natural log e is just 1.
Thank you very much. Equals natural log of, careful, 2 over 7 is at the top and 271 in the denominator, and we are solving for x dividing by this. We need to put everything in the calculator as is in one step, otherwise we introduce error. So when I divide these two fractions, I flip the denominator, so I have 2 over 7 times 271. So let me do this on the side one more time. So I had in the numerator 2 over 7, and the denominator was 271 over 1. So I had to copy 2 over 7 and multiply by 1 over 271. So then the numerator becomes 2, and the denominator I can change it into 7, 9, and 4, 1, 8. Or not. Sorry about that. So, yeah, so 2 times 1 and 7 times 1 is 7. 7 times 9 is 49. 9 and I carry 4. 14 plus 4 is 18. So this is what I put in the graphing calculator. Remember, parentheses around the denominator because of the negative sign. Otherwise, in this case, you would not need that. So natural log, I put this number in natural log, 2 divided by 1897, close the parenthesis, and divide by this number also in parentheses. Negative 0.122, close the parenthesis, and enter. So, according to the model, the age, years old, maybe I should say years young. So, it appears, if the model is correct, that when somebody gets to B56, if the model is still correct, about 70% of all people at that age, it's a huge percentage, about 70% of the people at that age have some heart issues. The percentage is 70%.
And that's a maybe obvious question, but not obvious to me.
Oh, any question, of course, please.
So when you divide by 271, I'm curious as to why that joins the 7 in the denominator when later you divided by negative 0.122. That became the new denominator.
Very good question. I see what you're asking. Very good question. Okay. So I'm assuming that, and you correct me, I'm assuming that this is clear. This step is clear. When I subtracted 1 and I got 2 over 7 and I have 271 here and E. Is this okay?
Yes, that's okay.
Okay, perfect. Now, I have to divide first by 271, correct? I can't apply the natural log I mean, I can apply it to a product, but it becomes more complicated if I don't solve for this first.
Right.
So then I have this. At the top, 2 over 7. In the denominator, 271 over 1. I cannot write the equal symbol again. Each equation has left-hand side, right-hand side in equal symbol. But I should write one more time. E to negative 0.122x equals 2 over, and we have that number, right? 1897. Is this better? When I divide 2 over 7 by 271 over 1, I copy 2 over 7, I flip 1 over 271, and I get this.
Okay. Is that because when you divide
Two fractions?
you're really multiplying by
Yes. Yes.
reciprocal?
Yes.
Okay.
Is this okay so far?
Yeah.
So now we apply natural log to both sides. We get negative 0.122x. I should write times natural log E, but that's 1, equals natural log of 2 over 1897. Now I cannot separate anything from here. This is just one single number. I can't do anything to it. It has to be in the numerator, and this number has to be in the denominator. So now I write it like this before I even look, because I may be tempted to do something else. Oops. Sorry. So that's why this is compact. I cannot separate the natural log from that. So that's why that becomes the numerator, and this is the denominator. We can approximate this and get blah, blah, blah. But if we do, we will have some more error at the end. That's why I want to keep it as is. But this is the quantity that makes the numerator. And then this is the quantity that goes to the denominator.
That makes sense.
Is it better now?